Coefficient of determination is one of the measures we use to determine which regression fits best. Here's an example. This is from the last video. So we already have the exponential regression. We already have the power regression. Graphing them both. Let's get the linear regression now. Let's do a quick linreg. There's our linear regression, and we can graph it also. There it is. So now we have the full set of three, at least that we do. I mean, there are other regressions, but these are the three that we're going to cover in this course. So the question is, which of them best fits the data? We use two measures, or two factors to determine this. Coefficient of determination is one of them. Residual plots is the other. This video is just using the coefficient of determination. Second, in the next video, we'll talk about residual plots. Now, the coefficient of determination, right, is known as r squared. The equation, one of the forms of the equation, is this. You'll also see it in textbooks sometimes as that, and sometimes as that, just so that you know that, in fact, they're all pretty much the same thing. SSE, the E in SSE stands for error. This part, y minus y hat's the prediction, so the difference between actual and prediction is known as error. This T, I think, stands for total. I'm not exactly sure why they use the word total. This is the difference between our data and its average. So what we're doing is we're finding the ratio of the error to the average. I like this equation the most, so I'm going to show you how to use this one. All right, I'm going to do this in my TI-84 using my stat lists. Notice that this numerator is an L3. This yi, right, is my y values, which is in L2. Y hat, I'm using the exponential one, which is why I'm using y1. I'm going to have to do this 3 times, because then I'm going to have to move on to y hat 2, y hat 3, right, to get a coefficient determination for each one. So this is what I get when I run L3, and what I need is y bar for L4, which is why I'm doing this 2var stats, and I can get my y bar, I can plug that into L4, and I can get my L4. Now it's just a matter of summing L3 and L4, which looks something like this, and gives me an r squared, or coefficient of determination, of 0.81. Now I have to do it for the power regression. Fortunately, I don't have to go all the way back to the beginning because my y bar doesn't change. Right? It stays the same, so all I have to do is change that y1 to now y2 so that I'm using the power regression. I get my L3, sum L3, and that gets me my coefficient of determination for the power regression. Now I can do the same thing for L or y3, which is my linear regression, and I get 0.72. Now for coefficient of determination, r squared equaling 1 is a perfect fit. You never really get that, but it's a perfect fit. R0 is no fit at all. There are no negatives because, of course, we're squaring, so you will never get a negative coefficient of determinations from 0 to 1. And because of that, it seems like our exponential regression seems to fit best at the moment because it has the highest coefficient of determination. Remember that that's only one of 2 that you need to determine the best fit. We do still have to do residual plots, but as I said before, that's going to be in the next video. Now, once you have your coefficient of determination, there's actually something really cool you can do with it. You can interpret your data using it. The way this would sound, right, is that 80% of the changes in your y value can be explained by changes in your x value when using an exponential regression. Of course, the same can be said for the power regression, only at 68% of the changes, and also for linear, where it's only 72% of the changes in y can be explained by changes in x, which is why, of course, we chose exponential, because it's the highest. Now, usually you're given some kind of context in these questions. There was no context here, so maybe we'll just make something up. Maybe these are ages, and these are heights. Of course, it's a little strange. People can't be -5 years old. So maybe our origin age is 13 years old. Right? And so this is 5 years before age 13, 10 years before age 13. And the same thing, this is the height at age 13. You can be greater than the height of 13 or less than age of height 13. Yeah, something like that. Just an example. So what you should do when you have context is say it using the variables. 81% of the changes in height can be explained by changes in age when an exponential regression model is used. Now, there's some subtle points with the calculator that are actually a little confusing. A lot of people don't understand it in the beginning. If I do an exponential regression, I would have to do it using L1, L4, because I couldn't use L2 because they're negatives. Right, I get actually an r squared. Right, if your diagnostics are on, the regression functions will give you r squared of 0.42, which of course is entirely different than what we got by hand. Well, it doesn't make, it's not too hard to understand, because of course that's using the transformed data, where the 0.81 is using the original data. So maybe what we should do is another example. An example that perhaps we don't have to transform, because there's still an issue that we have to talk about. And we can quickly go through and do our exponential regression, and there's our exponential regression, and we can get our coefficient of determination, and it turns out to be 0.81, or sorry, 0.89. This is a new example. And now if we use the calculator, we can do exponential regression L1, L2, because it's all positive. And you'll notice that the equations actually turn out to be, nearly identical. There's a little less rounding in the calculator. But the coefficient of determinations are still different. The reason for this, and this is just how the calculator is programmed, is that when you use the exponential regression, it calculates the coefficient of determination for the linearized data, which in this case would be like L1, L3, where when we did it by hand, we were really using L1 and L2, which is the original data, and it gets us a slightly different coefficient of determination. So which one can you use is the obvious question. Well, it depends what you're doing, actually. The one that the exponential regression function spits out at you can be used to choose the best fit. If that's the one you're comparing, the three different regressions, the highest one, or the one closest to the value of 1, is going to be the best fit. But you can't use it to do that interpretation, where the coefficient of determination based on the original data can be used to choose the best fit and can be used to interpret all the variables. So really, the one that uses the original data is better, because you pretty much always want to interpret at the end. If you're given an abstract question where you don't have any context, then I suppose using the regression one would be fine.